Imagine an infinite field of snow extending throughout all of space. Flat, featureless, going in all directions. Maybe the middle of Siberia. Now imagine that you're trying to cross this field of snow. So maybe you're a skier and you skim across the top. That's like a particle that does not interact with the Higgs field. It doesn't sink into the snow. It goes very fast. That's like a particle with no mass traveling at the speed of light. But maybe you've only got snowshoes. In that case, you sink into the Higgs snow field. You get less speed than the skier, less than the speed of light. That's like a particle with mass because you are interacting with that Higgs snow field. And then finally, if you've just got boots on, then you sink deeply into the snow. You go very, very slowly, and that's like a particle with a big mass. So think of this Higgs field as being like this universal field of snow. Now, where does the Higgs boson come in? Well, we all know what snow is made of, right? It's made out of snowflakes. In the same way, this universal Higgs snow field is made up out of little quanta. Those quanta are like snowflakes. That's what we call the Higgs boson. The Higgs boson has this job of giving masses to all the other elementary particles. If you look at the basic equations of the Standard Model, as written on my T-shirt, they're very symmetric. The way in which all the different particles appear is the same. At least on the top two lines, there's nothing to distinguish particles which have different masses, for example. But this symmetry has to be broken. Electrons are lighter than muons. The top quark is much heavier than the quarks that make up everyday nuclei. So the top two lines, the symmetric lines, cannot be all there is. There has to be something to distinguish between the different types of particle. And that's the job of the Higgs boson. That's the job of the two bottom lines. Depending on how those different types of quark, or the electron and the muon, depending on how they connect to that Higgs field, that Higgs boson, we believe they get different masses. The symmetry between these particles is broken.
Rumours about imminent results on the Higgs boson from the Large Hadron Collider experiments are appearing in blogs, social media and newspapers all over the world. Meanwhile, thousands of physicists are carefully analysing the data, looking not only for the Higgs, but for many other new phenomena. First of all, the data had to be collected.
The beams have particles and they are colliding, and we detect the products of these collisions in the different subdetectors that form a CMS. So it means that since the collision takes place until all the signature is recorded in a tape, this is the process of data taking. When the collisions take place, we need to have a very fast system that decides whether this collision is interesting or not.
These data have then to be reconstructed using complex algorithms and the massive computing power of the grid.
The data that we actually collect from the detector is raw data, which is just millions of voltage readings from all the different parts of the detector at the time that we had a collision. And so what we want in the physics analysis is more the reconstructed particles, so the energies and directions of the particles coming out of the collision. So we go from this raw data to this reconstructed data by running very sophisticated, complicated computer programs over the data in order to try and reconstruct the particles coming out of the collisions. And then this is what people use for doing the final physics analysis, for trying to find evidence of the Higgs or this kind of thing. They use these reconstructed particles.
Then comes the data analysis, where the physicists search these events, looking for gems in a pile of rubble.
So physics analysis is the process of taking the billions of events that we've recorded and trying to look for patterns, to sift through them, to look for interesting events, to look for unusual events, and to look for patterns like a clustering of events in mass. In the billions of events, we have perhaps a few thousand top quark events, for example, or perhaps just a handful of Higgs candidates if the Higgs boson exists. Other processes can accidentally mimic the same signature that we look for, these patterns that we look for, that may be produced by a top quark or a Higgs boson. And trying to prove that we all understand all of this, and proving also to our colleagues within the experiment that we understand all of this. So documenting it, discussing it together, reviewing it, and so on, so that we're confident when we go to a conference or we put out a paper, we fully understand the data and we can draw a firm conclusion.
Let me give you an example. Imagine you take a photo of a rabbit in a tall grass. It would be very hard for you to spot this rabbit immediately. Now imagine that you take 20 more photos of just random landscape and you superimpose them on the picture of the rabbit. It will be even harder for you to spot this rabbit. And that's exactly the situation we are in, because accelerator performs so well that we get many additional collisions with the main collision where we want to find something interesting. If you know that rabbit is under the tree, we basically hide the part of the photo which contains the tree. Now what we want to do is to figure out where the rabbit is within the grass, between the long grass stems. And what we are trying to do, not looking at the place where rabbit is to figure out how we identify these stems. If we can remove the grass from our view, we basically would have just the rabbits.
I think the most difficult thing at the moment, for example, is the time pressure. We've got all of this wonderful